Okay, uh, let's start with our, 1 second, let's start with our third video on this slide, starting from your 14th slide. Okay, again, going back to our model, we will have the extravascular model, XB, XGI, and again this could be, as we said in some references, TB, and this in some references TGI, as your X is D in some reference. Okay, so let's go back to the change in the amount on the body at certain time, and change in here, which is involving increase in this and decrease in this. So as we said before, rate of absorption, okay, minus rate, oh, I forgot the mic a little bit, okay, and rate of elimination, okay, which will be equal dxgi, whatever I said before, minus dxe over dt to give you the rate, the change, and the amount in the body. Okay, if we are talking about first order kinetic, until here we said it's true, either if we're talking about first order kinetic or not. If from now on, if we are talking about first order kinetic, this will be for first order constant, okay, and for first order constant, because we are talking about first order kinetic. So this will be positive Ka multiplied to xgi minus K multiplied to xb at certain time, dxb over dt. Notice that here this is a rate of change or mass over time of the amount of the drug in the body, or its plasma or serum is measured. We have it as rate of absorption minus rate of elimination. This part is whatever you know already from the IV bolus, or similar to whatever you know from the IV bolus, as I mentioned earlier. If we go back to whatever you know in the profile, again, this is what you have on your slide 15. You have amount at certain time versus time. بغض النظر whatever the unit that we have, we will have increase and decrease if we are talking about the conventional or the common case and kinetic, in which the absorption rate is higher or larger than the elimination rate. Here we said that this is the absorption phase. We have the maximum, we have the post-absorption phase, and we have the terminal phase or the elimination phase, right? Again, absorption phase, maximum or peak, and we have the post-absorption phase, and we have your terminal phase or elimination phase, right? If we are talking about this, then Ka xgi will be higher, okay, than K multiplied to xb, right? Here, two rates will be equal, or change will be equal to 0. So Ka xgi equals K xb, right? This is equal. Here, we will start to have decrease in the absorption rate. Ka xgi less than K xb. Terminal phase, you'll start to have elimination only because the absorption tend to be 0. Then we will have only K multiplied to xb at certain time. Again, this is what you know already. It's just only elimination. And this is what you have in your slide 15. Okay, now we will use this, which is your differential equation, and I need to have the model equation, right? This is the differential term of it, or differential um, picture of it, okay? So this is fifth, this is sixth. So again, if we go back, I will write it again. So you will have dxp at certain over dt equals dxgi over dt minus dxe over dt. We will have kaxgi minus kxp, right? This differential equation, usually we do integration, okay? When the equations in kinetics start to be more complicated compared to whatever that we know that is easy, and you can do it with the integration rules that we already know. We have Laplace functions or Laplace regulations or rules, in which Laplace is scientists that use different kind of rules to make it easier for a differential equation to turn into an equations or functions that we can work on, okay, and use the parameters as we did. So we have differential equation, and I need to have the function that I can use after I do the integration. So this kind of thing with Laplace, it become easier as it's having some rules to make it easier for more complicated equations, differential equation, to be transferred or transformed. Now we use softwares to make those rules of Laplace in the built-in in the software, so we can use it directly. This is a differential equation. After I do the Laplace integrations, it will be equal to and multiply to 2 exponential term, okay? Again, this we said that will be equal to this fraction of the drug bioavailable, the dose, first order rate constant. Again, to have this equation by default, I said we started with first order kinetic, right? So this is an assumption that we have, and we are still talking about first order kinetic in one compartment model, okay? So it's first order. We have first order rate constant of absorption, first order elimination rate constant. We have x naught gi, which is fraction multiplied to the dose. We have one exponent term that is related to elimination, and another exponent term that is related to absorption, okay? If this equation needed to be changed to the concentration, which is usually what we measure, what we need to do, you only need to have volume distribution, right? So if we divide the whole equation on the volume distribution, you'll have this. I divided the equation already, okay? Again, if you notice, we have this, this, and this as what? Constants. So whole term is consisting of different constant that we have, and we have by exponential term here, 2 exponential term. So usually you can find this in some references as A, which relate to the whole constant, minus Ka star. Okay, so this is the model equation, and you can have it like this in the term of the amount, or like this if we are talking about differential equation. Okay, that's why the equation is called by exponential equation, because it consists of 2 exponential terms. Okay, In your slide 19, you can find that I'm having, and again, this is just, let's say, illustration. If I draw the exponent term of any of those, so I will just call it star multiplied to t, or prime multiplied to t, versus time on your rectilinear. It's exponential, and this is minus. I'm just drawing the exponential term. I will have the faster exponential term at the beginning, okay? And then I will have, I need another color. So I will have this for the slower exponential term, okay? So this is a slower exponential term, and this is for the faster exponential term, okay? The general case, we said the general case, the absorption is faster. So usually this is related to the absorption, and this is related to the elimination. Usually, this is the general case. When we have the difference between them, it's similar to the idea of subtracting this profile from this profile to have this one, okay? To what you need to know from this slide take home message, that when we have the general case, that we usually have the absorption rate that it's faster than the elimination rate, which is the general case of the kinetic, and we will talk about this later. Okay, now we will talk about, it's already 12 minutes, so I will consider this about the I will consider this as the end of video number 3, to start with the method of determining parameters such as k and ka using some methods. So I will stop here and we will resume. Okay, bye.